All right, AP Calculus, semester 1, related rate, conical paper cup, 10 centimeters tall with a radius of 30. All right, and I kind of draw that picture right there. Little right circular cone, 10 centimeters tall and 30 centimeters radius. Not real realistic, but we can live with it. The cup is being filled with water so that the water level rises at 4 centimeters per second. Everybody, that's the HDT on my figure. At what rate is water being poured into the cup when the water level is 2 centimeters? Because it's going to change. So dVdt when H is 2. All right. You would be expected to do all this stuff just from the word problem. And the hard jump here is this. You have to know that for a cone, this is the formula. And this time the base shape is a circle. So we get this formula. And right now, my expectation as you get good at this is you would be able to look at this formula and recognize that the right side on the derivative is dVdt, or the left side is dVdt, but the right side is product rule, because R and H are both changing. And I do not have drdt. I just have dHdt. So I know right now I have to get R in terms of H and get R out of my formula. And you might look at this and go, darn, I don't see it. Well, the thing you got to catch is at any given instant that you're filling it, the R and H of the blue triangle has to be similar to the 1030 triangle of the cone itself. All right? And what I mean by that is if I pull it out of here is that these two triangles are similar. So their ratios are the same. It's like the torture from beyond because all of a sudden geometry matters again. So I know that the ratio R over H has to be the same as 30 over 10. And everybody, there were centimeters on both, but they can't. These are unitless ratios here. Cross multiply, well, yeah, I would just write R equals 3H, right? I would just multiply both sides by H, 30 divided by 10. I'm feeling great about this now because I can replace R. So before I even differentiate, I'm just replacing R with 3H and squaring it. Oh my gosh, we get so many mistakes right here. Everybody, that is 9H squared, not 3H squared. All right? So I get a formula of volume equals 9 times a third, 3 pi H cubed. And now I feel great. And guys, this is not the formula for every right circular cone. It's only for the ones where the radius is triple the height, which, by the way, is very odd. But this works, and now we should see the derivative. dVdt, derivative of v is 1. Derivative of h cubed is 3h squared times pi. 3 pi is 9 pi h squared, dh dt. And everybody, again, we get to a formula here where everything is known. So dVdt equals a little bit of math. 9 pi, the height is 2 centimeters, squared times 4 centimeters per second. Take 2 seconds to notice here right away. Centimeters squared is centimeters squared times another centimeter. Our units are cubic centimeters per second. That matches dVdt. So I feel really good that I didn't make a mistake. 4 times 4, 16 times 9. If it was 10, it'd be 160. Take away 16. How about 146 pi? Did someone else get that? Or did I make a math mistake? I don't know. I got checked 16 times 9. Oh, how about 144? I wrote 146. I think I made a math mistake there, right? 16 times 9. How about 144 pi? Does that look better? And cubic centimeters per second. Again, not a real realistic problem. That is a huge dVdt number. I mean, 3 times that is 300. It's about 450 cubic centimeters per, like 3.5 liters into a small, very oddly shaped circular cone. But that is the answer. And again, the big step on this one, before we go to the next problem, is making this happen. Knowing from the givens that we have to get rid of R, and it has to be done in terms of H. All right, last problem. We got a cube problem to work on. A perfect cube of ice melts at a rate of 27 cubic millimeters per second. Guys, you see the cubic millimeters? It's dV/dt equals 27. And everybody, it is melting. So we have to be negative. The volume is getting smaller. Doesn't say negative, but melting is negative. Assume the block remains, it's cube shaped as it melts. Yeah, that doesn't happen, by the way, guys, but we'll assume it. At what rate are the sides of the cube changing when they're 3 centimeters long? And again, this is the kip-off, what rate? So it's dx in my figure, dt. When x is 3 is the unknown. Again, two formulas for cubes we should be familiar with. We have already talked a little bit in my class about volume. Volume is x cubed. One of my favorite things is to relate volume and surface area. We should be able to look at this and understand that the surface area of the cube would be 6x squared. Because the volume of each surface is x times x, and there's 6 surfaces. I know that this time I don't need surface area. All right, just a chance for us to talk about it. And I can see right away, the derivative of v is 1, dv dt, 3x squared dx dt. And again, this is a pretty fast one. Negative 27 cubic millimeters per second equals 3 times 3 millimeters squared dx dt. And everyone, hopefully you see the units are going to be millimeters per second. Millimeters cubed divided by millimeters squared. 27 divided by 27. You can tell this is a book problem. And we get that the rate of change when the sides are 3 millimeters long is 1 millimeter per second. Literally, think about that. That's telling you that in roughly 3 seconds, that whole cube would be melted. Right? Because they're 3 foot long and they're decreasing by a millimeter a second. So again, it must be in the oven. All right? It must be in a very, very, very hot place for it to be decreasing this rate. But again, sometimes when we do practice problems, they're not the most realistic. Computer plugs in numbers into situations. But again, good practice. All right? Keep practicing. That's how you get good at things.